Hi, everybody. Let's go through chapter 1 lecture. And here we go. Okay, so the beginning of the chapter of any chemistry, intro chemistry class, of course, chapter 1 is just, to introduce you to chemistry. So you can see here, you guys can read, chemistry is the study of matter, and matter is everything. Even if you can't visually see it, for instance, the air that we're breathing right now, that's matter. It's a gas. We can't visually see it. Sometimes we can see it in terms of pollution in cities, and that's kind of gross, isn't it? But just because you can't see it, unless it's a true vacuum of space, there's something there. There's gas there filling up the space. You can see on the screen here, and again, as I said, I'm not going to read through all these slides to you. That would be quite boring. You can see examples, though, that matter can be natural, things that don't take man's intervention, and some that's natural, and synthetic would be, yeah, man intervened, a human being, I should say man as human being, intervened to create these substances. We know that matter comes in several states, solid, liquid, and gas. And solids, in terms of, what do they look like? If we could take a really powerful microscope and look at the molecules and the atoms, solids have a definite volume. They maintain their shape, and they're very close together. Whoops, you can see right here the example. This bubble is supposed to be, if you could look at something under a microscope, you would see that the molecules are very close together. They're in a regular pattern. They're not moving much. And can you change a solid? Sure, you can. For instance, you could take a piece of paper that's a solid and tear it up and cut it up. It's still the same thing. It's still paper. You haven't made any big changes chemically to it, but you can make changes. Liquid, again, definite volume. The quantity in terms of volume stays the same. Think about a 2 liter of soda pop. If you poured that all over the floor, the volume is still 2 liters. The shape is just a little different. Now it's all over your kitchen floor. And liquids here inside this bubble are also, again, still close together. However, they're much more random, and they're moving around more. And then, of course, our last shape, our last state, is what we got here, the gas state. Now, looking at this bubble, you can see huge distances between the molecules. Gases have no definite shape. So, for instance, you can take, maybe you've had a loved one or a friend that's had a tank of oxygen gas that they've needed for breathing. You can open up that tank and release the gas into the room, or feed it, through the patient, and it takes the shape of whatever the container is, the room or the cylinder of gas. No definite volume. That's the other crazy thing about gases. They're just like out of control. You can change the volume. So again, if we go back to, think about, whoops, sorry, hit my iPad here. I'm going to be really bad at drawing, but if we have this cylinder of oxygen, the volume in this cylinder, I don't even know what volume, maybe they're 10-liter cylinders that patients that need oxygen have. If you release that gas into the air in a room, there might be 10,000 liters of space of volume. So you can change basically everything about gases, their shape, their volume. In terms of their movement, I already said you can see they're very far apart here as compared to my last slide. And they're moving like crazy. And I always like to give the silly analogy, but it really does fit. Imagine a room of 2-year-olds who have had lots of sugar and candy, no adults, and they're in this room all by themselves. They can do whatever they want. It would be sheer chaos. That's what gases are like, just out of control, moving crazy, bouncing off each other, chaos. All right, let's talk about states of matter. So physical properties. This is a really big and important concept. Physical properties and physical changes versus chemical properties and chemical changes. So physical, you are describing something and the description is without changing the composition, meaning without changing what you have. And so probably my favorite example is to just talk about the physical properties of water, H2O. We can look up its boiling point, 100 degrees Celsius. We can talk even about its boiling, changing from a liquid to a gas. We can do the same for melting or freezing, which happens at 0 degrees Celsius, changing from a solid to a liquid. Solubility means some substances that will mix or dissolve, like salt dissolves in water. We can describe its color, its odor, and then talk about whether it's a solid, liquid, or gas. And all of these things I just described don't change or aren't talking about changing water in terms of the chemical bonds and the fact that it's still H2O, an oxygen connected to 2 hydrogens. So physical properties, you could also talk about your friend, what your best friend looks like, what they act like, physical properties. Physical changes, then talking about how we might change something, but not, again, not what it is. It's still, in all 3 of these little bubbles here, this is all still H2O, water. Whether it's a solid, liquid, or gas, you still have oxygen with chemical bonds to hydrogen. So you're physically changing what something is, whether you're melting, freezing, boiling, vaporizing, or even mixing it with salt. There's actually not any chemical bonds that are formed or broken when you dissolve salt in water. So those are physical changes. And of course, now let's talk about the opposite, chemical. Chemical properties describe or determine how something is changed from one substance into another. Properties describe changes. So a chemical change is the actual act of doing something. So I could say, as an example, chemical property, oxygen and hydrogen gas do react to make water. I could also then do that actual process, taking oxygen and hydrogen, doing a chemical reaction and forming water, a new substance. The act of actually doing it, doing a reaction, is considered a change. Properties would be a description. I could do this. This is what will happen if you want to do it. That's a property. Kind of some other things. Again, you always just want to focus on what you start with. Is it the same thing as what you end up with? On the left-hand side, you notice I have oxygen and hydrogen, the red and the whitish gray spheres, all by themselves. But on the right-hand side, now they're hooked together, and that's a chemical reaction. So physical changes, chemical changes go with an actual reaction happening. All matter can be classified as either pure or a mixture. Pure substances are only one thing. They have constant composition, meaning, again, regardless of how much or how little you have. Let's say you've got a container of pure distilled water. The top of that container has the same stuff at the bottom. Doesn't matter where it came from. You cannot take a pure substance and break it down by physical means to another pure substance. All matter, then, again, pure substances. Some examples: table sugar and water. They're both pure substances. Now, I'm not talking about mixing them. I'm talking about a container of sugar and a separate container of water. They are pure. Yes, I can break water down into its constituent elements, hydrogen and oxygen, but to do that would be the opposite of what we talked about over here. We'd be going in this direction, and it's still a change of what you have, meaning that would be chemical. And that's not what we're talking about here with these pure substances. So this is pure water, pure sugar. I can chemically do things and change it, but that's not what we're talking about. And we're going to get to mixtures, and it'll kind of make sense here in just a second here. Mixtures are mix those two things together. So take the sugar and take the water we just talked about and put them together, mix them. Now you've got a mixture. They have more than one, so 2 or more components. So I could put sugar in with water. I could put salt in with water. You kind of get where I'm going. Now, here's the crazy thing, and not always obvious to students. This is something you kind of have to just learn with time or ask if you're unsure. Mixtures can be separated into those original components like water and salt by a physical process. So in other words, if I have a container, and you can even do this at home if you have a pot of water, you could make salt water, Salt is sodium chloride, and H2O, sorry, you can hardly read that. If you put a flame to it and boil that, the water leaves as water vapor or steam. It evaporates. And at the end, and don't do this, your mom would probably get mad with her pot at home. At the end, you would have just pure salt at the bottom of your pot all by itself. So we're separating the mixture of salt water into its original components, or into its pure substance components, water and salt. So that also tells us it's a mixture. Please know this is physical, not chemical, because yes, water can be separated into its elements, hydrogen and oxygen, but it requires a chemical change in making and breaking of chemical bonds. Okay, big difference. And this can be probably really confusing for a lot of students. So when in doubt, always ask if you're unsure of something. All right, so here's sugar being mixed in with water to make a mixture. Now let's talk a little bit more about pure substances. Elements or compounds. Elements are those things on the periodic table. Those things cannot be broken down even with a chemical change. Even with a chemical change. Aluminum is aluminum. And I like to think about this. I have lots of analogies you'll hear this semester. I like to think of the analogy with elements and compounds. Think about Legos, those, the kids' toy, the Lego. You have the individual Lego pieces. This would be like your individual block of a Lego, one piece. That's the element. And unless you're gonna like get some tools out and smash that thing to bits and do crazy, crazy things, you can't break it down. And that's the same thing with an element. Truth be told, we can do things to elements to change them, but it's like getting a hammer out and doing something crazy. And in fact, it's called nuclear chemistry. So we'll learn about that in chapter 10, but up until chapter 10, we're gonna stick with the rule that one element can't be broken down or changed, and definitely never by a chemical process. So elements are my individual Legos, and a compound is, well, let's put a couple of Lego pieces together. Maybe I've got this red. You guys are gonna tell quickly I don't have good artistic abilities. And maybe you've got a blue piece of Lego, and you start hooking them together. And maybe you got a yellow. You guys know what I'm talking about, right? And so that would be my compound, joining two or more elements together, and you make this compound. Here's just the diagram, kind of that flow diagram. It puts everything together. Everything, as we said, is matter. And from there, it can go in one of two directions. It can go into the pure substance category, or it can go into the mixture category. Once you've got pure substances, then even further, decide if your pure substance is an element like aluminum, or is it a compound like water. Mixtures are made up of one or more elements put together, or one or more compounds, or combinations thereof. All right, now let's get into some numbers, everybody's favorite thing, right? So in chemistry, we don't just look at numbers. This isn't a math class. We're looking at measurements. And so you will see 9 times out of 10, these numbers have units, substances, things like that with them. And in here, this is so critical. Numbers are meaningless without the unit. And so you can see there on the screen, a proper aspirin dosage, 325. And you can't just say 325. What is that? Is it in milligrams or is it in pounds? A lot of you want to go into medicine. If a doctor tells you give the patient 325 aspirin, whoa, what does that mean? Individual aspirin tablets, milligrams, pounds? Units are critical. And then there's a second example there about the meter dash. But I think for everyone watching this, probably the point gets across real easily when we talk about 325 aspirin, right? Now in science, we use the metric system, and for each of these different quantities, you can see on the table what the base unit is. So length, base unit is meter, mass is grams, volume is liter, and time is in seconds. Does that mean it's the only unit we can use? Absolutely not. This is, I like to say, just the most common and what we tend to start with. Now from these base units, however, we can use the metric system and change things up a little bit, meaning, for instance, when you weigh a patient on a scale, if you're already working in a doctor's office, you know, you might weigh the patient at 52.5 kilograms, not grams, even though that's the base unit of mass. Well, but that would be 52,500 grams. I don't know about you, but I don't want to stand on a scale and see 52,500 grams. So we use these prefixes to make things kind of a little more manageable, I like to say. Do you have to do it? No. This is just kind of an abbreviated form. Instead of saying 52,500 grams is the patient's weight, we say 52.5 kilograms. Now, where does all this come from? Well, that K for kilo, that's the prefix, and it's 1,000 of the base units. So in other words, because this table can be kind of hard to follow, 1 kilogram is equal to 1,000 of the base unit grams. So kilos are really, really, really big. Grams are much smaller. Now, I'm just going to talk about two of them on here because I want to go in each direction. Both this is above the number 1 and this is below, and again explain how I kind of write out conversions. So that's the example for kilogram. But if I wanted to do milligrams, like a dosage for the aspirin, 1 of the base unit grams equals 1,000 milligrams. So, whoops, and you guys, I'm sorry, I'm writing with my Apple Pencil and it doesn't always come across there. That's a little prettier, a little more legible. So milli are really, really tiny. Like you would give the patient an injection of 0.1 milliliter. You wouldn't give the patient 1 liter of a drug. Now you might give them 1 liter of IV solution. That's a much larger quantity. That's one of those big IV bags. But dosages for drugs, things you're giving them on a much smaller quantity, you will see the milli is used, whether it's milligrams or milliliters. And again, when you're weighing patients, we're going to go to the big numbers, kilo for kilo, kilogram, or kilometer in terms of driving. So again, here you can see how it's broken down. I hate decimals, and I know students don't usually. So you'll see that I write it out 1,000 of the milli, whatever the base unit is, we'll just call it milli X, is equal to 1X. So 1 milligram is equal to 1 gram. 1 milliliter is equal to 1 liter. Same thing with centimeters. I hate fractions, and I know most of you guys do too. So, whoops, I just wrote that wrong. Get my eraser here. Hang on, I'll fix it. So 100 centimeters equals 1 meter. So you can look at the conversions that way. If you like the decimals, that's fine. It's 1 of the unit we're talking about, centimeter, equals how many of the base unit. So you can do it either way. I just find students tend not like to use numbers less than 1 if they don't have to. Here it is for mass. Keep in mind, there is a difference between mass and weight, and we interchange the words a whole lot. You may even hear me interchange them. It's just habit from living in society. We talk about it like that all the time. Mass is actually the measurement of the amount of matter in an object. Mass never changes. Whether you're here on Earth or whether you're up in space, your mass is your mass. Weight, however, does change because weight is based on gravity. So that's why we'll talk about mass of a substance or of matter in this class. Try to just use that word. The base unit for mass, as I showed you a few slides ago, is grams, but those prefixes, the cool thing about the metric system, these prefixes apply the exact same way, whether you're talking about grams or meters or liters, it's all the same. 1 kilo of whatever equals 1,000 of the base unit. 1 kilogram equals 1,000 grams. 1 kilometer equals 1,000 meters. 1 kiloliter equals 1,000 liters. And hopefully that, you see where I'm going with that. Same thing for milligrams. Same thing with any of the prefixes. They apply exactly the same. And a lot of us in the United States here struggle with metric system because it's just not something that we use. We don't use kilograms for our weights. The average American talks about pounds. We have the US system. So unfortunately, that means that students often struggle with going between the two, or just even, in a college class in Europe on chemistry, they wouldn't start with the metric system and the prefixes. They would assume students know how to do that. Just like I'm not starting with how to convert minutes into hours. You guys know how to do that because you've been doing it since you were in kindergarten. But here we don't use the metric system as our unit, so we've got to spend some time doing it. All right, when we talk about volume, the base unit is liters. So again, I'm not going to beat this dead horse here. Kilo and milli mean the same thing. Now, one other thing about volume, and that is, if we talk about, for instance, the volume of space that a cube or a block occupies, we can take a measurement with a ruler and measure the length, the width, and the height of that block. And if we use the unit of centimeter, and technically you can use whatever unit you want, but when you multiply the three together, you compound those units. In other words, it becomes centimeters cubed, or cubic centimeters is how we actually usually pronounce that. So centimeters, anytime you multiply units, you add them up. So I have 3 centimeters I'm multiplying, so I have cubic centimeters. Now, to keep things a little easier for us, 1 milliliter actually equals 1 cubic centimeter. It's a 1-to-1 ratio. You might also, in medicine, they talk about give the patient 5 cc's of, the drug. Well, cc is the abbreviation for cubic centimeter, and so that's also equal to the same thing. All right, here's just some conversions for between, as I said, the English or US units and the relationship between them, because we use our own special units here. I think it's important to point these out. You always have access to this list. You always have access to it. So if you need to go look something up, go look it up. Some of them you might already know in your head, just depending on, if you're already working in a doctor's office, my guess is you probably know this one right there already. If not, go look it up. You're going to learn in a minute how we apply them, and you'll see no matter where the conversion, or these are also called equivalents, you'll hear me use the term conversions because they allow us to convert. One and the same thing, no matter where you get these equivalents or conversions from, whether it's from your memory because you have used it enough that you know, or whether it's you have to go look it up in a book or look it up on Google, they're applied exactly the same way. So not to panic, okay? And we'll get to some of those examples in a minute. Let's talk about sig figs. Exact numbers versus inexact numbers. Exact numbers come from when you count something or as part of a definition. So any of these equivalents, I'm going to abbreviate, or what I was calling conversions, those are exact numbers. If you grab a meter stick, you can count 100 centimeters are notched off on that meter stick. If you count your fingers or your toes, again, that's an exact number. Inexact, as you can see, inexact numbers come from a measurement that's been taken, and those measurements contain some uncertainty. Just think about using a ruler, this is going to be kind of a wimpy little example here because I'm not going to make all my, but and we can even talk about inches. Let's say these hash marks are inches, which means this would be 0.5, this would be 1.5, 2.5, 3.5. And then let's say that, you're measuring the length or the width of a piece of paper. You're measuring some object like that. And that's where it measures at. And you might look at that and say, hey, I think that's I think it's 2.6. And your friend might say, no, I think it's 2.7. Well, that's where this uncertainty comes. The last digit is always the uncertain one, and it's based on your given tool. So my little wimpy ruler that I just drew here doesn't have lots and lots of these hash marks. If it had lots of hash marks, I could measure it with a little more certainty. No, those weren't there. So I was just kind of estimating somewhere between 2 and 3. It was more than half, and so that's okay. That uncertainty is always the last digit. Now, in terms of sig figs, what I then find with students is that they struggle, and really I can't say it's just, truth is, the challenging part is, what do you do with the non-zeros versus the zeros? And the non-zeros are easy. Non-zeros are the digits 1 through 9. And if you have a measurement, you take a measurement, you're given a measurement, and you have a digit 1 through 9, That's considered significant. It's important. We're going to count it. You go, okay, Dr. Liz, well, what if it, what? Well, here's where the tricky part comes in, and that is, what do you do with the zeros? Well, if there's a zero, and if you think about a number or a measurement like a sentence, you know, we read sentences like I'm reading this sentence, a zero counts as a significant figure. We read sentences from left to right. Sentences have beginning words, you know, this would be a beginning word, it's got some middle words, and it's got, you know, wherever I'm going to end it here, I guess there's the ending word. Beginning, middle, and ending. Numbers are exactly the same way. Numbers have beginning, they have middles, and they have ends. So think of it like a sentence. And we're going to talk about zeros as being either beginning, middle, or end. So here's the deal. If they're between, that would be a middle zero. Middle zeros are always considered significant. Okay, so I'm going to actually break this down, break the rules for zeros down even further. Middle zeros are always considered significant, meaning when you're adding up how many sig figs are here, like in this example right here, that zero that's in the middle, 29.05, that zero is considered significant. And we would say that measurement has 4 sig figs. Over here, hopefully then you can see those are middle zeros. They count. That measurement has 5 sig figs. Now, at the end of a number, let me come back up here to my little table. Zeros at the end are sometimes, that kind of stinks, doesn't it? Are sometimes counted as significant. Here's when they are significant, and that is if you have a decimal. So in fact, let me change this. I'm going to get a little more specific. Zeros at the end of a number will be considered significant. Yes, they are significant if there's a decimal anywhere in the number. So this example here, 3.7500 centimeters, these zeros are at the end, but there's a decimal in the number. So yes, decimal, yes, they're significant. So 1, 2, 3, 4, 5 sig figs in this measurement. So beginning, middle, and end. This slide so far only talks about middle. Middle zeros are always significant, whether there's a decimal or not. Doesn't matter if this was my number, 2,905 grams, that's still a middle zero. That measurement still has 4 sig figs. Ending zeros have a decimal anywhere in the number, then yes, you count those zeros in your count. All right, here's when it doesn't count, and that is if they're at the beginning of a number. And you can see some examples here. Again, think about these like sentences. You read from the left to the right. And if you start reading a zero, 0.00245, if I start my sentence with a zero, I do not include those numbers as significant. So I come back here. I'm going to keep going with my summary table here. Beginning zeros are never significant. Middle zeros are always significant. And ending zeros are sometimes. If there's yes a decimal, then yes, they're significant. But if there's no decimal, they're not significant. 2,570, no decimal, no count, I like to say. So no decimal, they don't count. Okay, so please, please, put this somewhere. This is a real basic breakdown, but this is the rules broken down in a summary table. Now, before I go on beyond this, let's talk real quickly about what does that mean that they don't count? What does that mean? Does it mean that this isn't the measurement? Oh, that's absolutely the measurement. Here's the measurement in volume. It's that those zeros are placeholders, because for those of you that know about scientific notation, which I'm going to get to in just a second, I can write this measurement like that, 8 times 10 to the minus 3. Those were just placeholders. Yes, it's important. Yes, it's part of the measurement, but I could write it out and those zeros drop off. I'm just holding a place to write a decimal notation number. When I take that number and I write it in Scientific notation, instead of decimal, I don't show those because they were just holding a place. Still important, it's still there. Just like down here, I could write 2.57 times 10 to the 1, 2, 3, positive 3 meters. And notice the 0 just dropped off. It's still there. It's still a measurement of 2,570, but in decimal notation, you include it, and in scientific notation, you can take it off, okay? It's just a placeholder. So not to be confused, think about your bank account. If you had $2,570 in your bank account, that doesn't mean you have $257. No, you have it. You're just, usually that's just kind of an estimate. Because get this, if I talk about money, if I said I had $2,570 in my bank account, if that's what it was, exactly, like I went to my bank and I found out that's exactly what I have, well, guess what? 2, 4, that's 6 sig figs, because I put that decimal there. And if instead I just said, how much money in your bank account? And you said, I don't know, around 2,570, you're just guessing, like you're rounding, you're estimating. I don't know where you're estimating. You could have more than that. You could have a little less than that. This only has 3 sig figs. You just know we're in this ballpark somewhere. That 0 is not, you're not putting a decimal there and saying that's exactly what I have. You're saying, nah, that's approximately what I have. Okay, now let's talk about sig fig rules and multiplication and division, and we're gonna do addition and subtraction. So lots of, times, 9 times out of 10 in here, when you're working problems, you're going to be, doing math, applying math to a problem. And so in this example, we're taking miles and we're dividing it by a time in hours. Your final answer, well, first, plug that in your calculator and hit the equals button, and your calculator is going to spit out some big long number. And then inevitably you say, Dr. Liz, how many sig figs do I need to write down, or how many digits do I have to write down? Well, use your rules. And the rules for multiplication and division are the following. Look at the measurements, not the conversions or not the equalities, because those are exact numbers. Look at the measurements and how many sig figs does each measurement have based on the rules we just covered. This one has 4, the bottom one, 5.5 has 2, and you go with the fewest sig figs. So you need to take 63.854545 and bring it down to just 2 sig figs. Whoops. And so that means, okay, 2 sig figs means I drop it there, but you don't just drop it. Remember our rounding rules. So you look at what you're going to drop and say, okay, is it 5 or above? Then I'm going to round up. If it's below 5, I round down. Well, it's an 8. 8 is between 5 and 9. So I'm going to round 63.854545 up to and report my answer as just 64 miles an hour. So always look at the measurements given, and however many the measurements have in terms of the lowest, that's what you should have. All right, and so there's just a summary depending on where you were dropping it, like that, or right here, or right here, or right here. What it would look like in case you need some additional help. All right, addition and subtraction. A little bit different process mathematically, a little bit different in terms of the rules. This one, you look at numbers past the decimal. And you still go with the fewest or the lowest. 10.11 has 2 past the decimal, 3.6 has 1 past the decimal. So 2 versus 1, 1 is lower. So the answer, the final answer you report, this is probably what your calculator is going to spit out at you, but what you circle and turn in and tell Regis this is your final answer can only have 1 digit past the decimal, because this only had 1. And yet our rounding rules still apply. So you go, okay, I can only keep 1 past the decimal. I look at what I'm going to get rid of and I say, is it below 5? Yes, so I'm going to round down and I'm going to report just 6.5. Had that been 6.56 kilograms, do you know what we would have reported it as? Yeah, we would have rounded up to 6.6. You look at where you're going to drop, You look at where you're going to drop and say, okay, I got to drop this. What is that first digit? The very first digit is 5 or above, you round up. Below 5, even if it was 4, 9, whatever, that you look at that very first digit right after the dropping point. All right, scientific notation. Hopefully you guys should have a good handle on this from your previous chemistry and math. Basically, scientific notation takes a number and it's just like an abbreviated way to write it. You start with a number, not a 0, a number between 1 and 10, and then you say multiplied by 10 to some exponent, and the exponent can be a positive, that's if it's a really big number, greater than 1, or the exponent can be negative, and that would be if you have a number less than 1. That doesn't mean it's a negative number. The positive or the, whoops. Uh-oh, it's not letting me write. What's going on? Oh, I'm locked up. Hang on, guys. The positive or negative would go out in front. Uh-oh. All right, hang on, I'm locked up. I got to sign off and sign back on. Let's try this again. Ah. Sorry, the computer does this sometimes. Oh. No, maybe my pen might be, my Apple thing might be dead. We'll charge it for a minute. So the positive or negative, I'll have to write with my finger for a few minutes here while it charges. Positive or negative in front of that would be if you have a positive or negative number. Positive or negative exponent has to do with whether the number is above 1 or below 1. And I'm going to show you some examples. So for instance, 2,500, even though there isn't a decimal there, we're assuming the decimal's right there. And if I want to make that into the shorthand method, that means I'm moving it 1, 2, 3 spots. That's where the exponent 3 comes from. And because it's a big number, I always like to say, like, you know, think about your bank account. If that was your balance or your deposit you were making in your bank, that'd be a positive thing. Like, you'd be happy about that. So the exponent is positive. And if it's here's my less than 1. If it's a little tiny number, you still think about moving the exponent, or excuse me, moving the decimal between the non-zeros. So you'd move it between the 3 and the 6. I did 2 hops to get there, but this is a small, tiny number. Definitely would not be a good thing if that's what's all that's sitting in your bank account. So it gets a negative exponent. Okay. Just some more examples here of if you're given and you're given scientific notation and you have to write it as a decimal. Again, think about if it's a positive, you're going to be making a big number, bank account number. If it's negative, oh, that would be bad, little tiny number. And the number is equal to how many hops or places you move the decimal. All right, probably the most challenging part of the chapter for everybody, conversions. I showed you those conversions. They're also called equalities, one and the same thing because they're equal to each other. And you've done these. You guys, you've done these in your life. If I asked you right now how many minutes is in 2 hours, you might even have to grab your calculator or scribble something down, but in 2 hours, there's 120 minutes. And you know that, and you can do it because you've done it a lot, and because you're comfortable with knowing that, hey, I don't need to go look up a conversion. I know that 1 hour equals 60 minutes. So 2 hours, 2 times 60 is 120. And we just did this talking aloud in your brain without having to show anything kind of fancy, because you've done it. The same idea is going to apply here, with the exception that you'll probably have to go look up the conversion factor or look up the equality, because you might not just know it without looking. And that's okay. The mathematical process is still exactly the same. Now, the books usually talk about fractions and which way do you want to write the fraction? Well, let's just forget fractions, okay? Let's just talk about how we're going to do this regardless of what the original quantity is and the desired quantity. And that'll make sense in just a second here when I work this out. So here's the problem, and you can read about factor labeling and all that later, but here's the problem in the middle. To convert 130 pounds into kilograms. So what's given in the problem? There's my original quantity in unit, 130 pounds. What are we looking for? What's the desired? We're looking for kilograms, a number in kilograms. So you always set up the problem, what you're given or what's original first. And I always put an equal sign and then write what I'm looking for. I'm looking for conversions. Now, here's where I'm going to vary a little bit with my method compared to the book. Again, the book always wants you to think about fractions. And I hate thinking about fractions. I like to do something, and I like to do it the same way every single time. So what I would do here is I'd set up this conversion factor, and I've got it. Let me see if I'm going to give myself a little more space. Let me write it out a little better because I've got that box there in the middle that says conversion factor. So let's just write it out. This is what I would do. I'd set it up like this because I know I'm going to have a conversion. So I put that line there. That's the fraction though, but let's not use the word fraction. I want to get rid of pounds. That's what's given. Whatever you want to get rid of in the conversion, you put on bottom. Think about it like, you have a pile of mail sitting on your desk. I always put the bills at the bottom because I want to get rid of them. I don't want to see them. Put it on bottom and cover it up. What do you want? That's your desired quantity, whatever you want. Like I want to look at my home and my HGTV magazine. I'll put that on top. It's much more desirable. So what do you want to get rid of? How do you know what you want to get rid of? It's all based on the original. The original is in pounds. So I want to put pounds on bottom because I want that to cancel when I do the math. And anytime you have something in the numerator and in the denominator that's exactly the same, it will cancel. Whether you're talking about, think about this, 5 over 5, the 5 on top, 5 on bottom, cancel. Or whether you're talking about units, pounds on top, pounds on bottom, cancels. So you always set it up so that what you're getting rid of goes on bottom, what you want goes on top. Because then when I do the math, what's left is what's on top, and that will be what I need. Now from here, this should be the most difficult part of it all. And that is you have to find the conversion factor, the equality. You have to find the equality. And did I have it on that last slide? Yeah. And here was the equality. 2.2 or 2.21 pounds equals 1 kilogram. So I come back here. 2.21 was with pounds. So I find a unit of pound, and I just stick the number right in front of it. And the number 1 was in front of the kilogram. And you always keep the number tied to its partner, tied to the right unit. The 1 is with kilograms. The 2.21 is with pounds. Then you don't have to think about, well, which number goes on top, which number goes on bottom. Follow the units. Set the units up first based on what you're canceling, getting rid of goes on bottom, what you want goes on top. And then go to that equality, whether it be something it's just in your brain, or whether you have to go look it up, and always keep the number with the unit. And then what do we do? Last step, multiply if it's across the top, divide if it's on the bottom. So this will be 130 times 1 divided by 2.21, which I get in my calculator 58.8238. Oh, lots of digits. That's what my calculator gives me. But remember, now we're applying 2 things, problem solving conversions, and don't forget what we just talked about, and that is sig figs. There's my measurement. The patient's weight was 130 pounds. Do you know how many sig figs that is? Well, remember our 0 rules, no decimal, the 0 doesn't count. This is 2 sig figs. So 1, 2, I'm gonna have to cut it here. So look at this first digit that I'm about to drop, an 8, and say, oh wait, that's above 5, excuse me. So 58.8235, blah, 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 is going to become, I'm gonna round up, 59 kilograms. And that's how you report the final answer. Again, this talks about, think about your fractions. Forget the fractions. Use that same process every single time, and I promise it'll work. So why don't you guys try this one? How many grams of aspirin, so this is the desired, are in a 325 milligram tablet? That's the given. I like to call it the given. You could also just say it's the original. So you're going to set up with your given 325 milligrams. My basic kind of setup here. Start with your original. Put your line equals what you want. What you want to get rid of, the unit put on bottom. What you want, the unit put on top. I want grams. I want to cancel my milligrams. Go find the equality. How many grams is equal to a milligram or whatever, however you want to say it? Well, 1 gram is equal to 1,000 milligrams. Multiply across the top, divide on the bottom, and you get 0.325 grams. Now, sig figs, that's what we get in my calculator when I do the math. Let's check our sig figs. 1, 2, 3 here. The beginning zeros, remember, never count. 1, 2, 3 here. So that is my final answer. Let's see here. Always arrange the factors so that your denominator, so what's on bottom cancels what's on top. And again, guys, if you're using my method, you don't have to think about 2 fractions and go, well, which fraction will work? Forget that. Set it up so that you cancel what you don't want, you get what you do want. Now, I'm going to explain this one in just a second, but so this is a 2-step. I've got this first conversion factor or equality, and I have this second conversion factor or equality. And before we do one that you might not be familiar with, let's do one that you are familiar with. So across the bottom here, I'm going to do one. How many seconds are in 2.5 days? Okay, so let's say that's the one we're going to do. And I really want to do it here on the same slide because I want to show you that regardless of what you're doing, I'm going to give myself some more space up here to write. No matter what you're doing, whether it's pints to liters or days to seconds, check out the setup and the process is exactly the same thing. So my given is 2.5 days. And if you didn't know it's 2 steps, you might set it up and start just like we did before. You know, you go, okay, I want to put days on bottom and I want to put seconds on top. And hey, maybe you're really, really good and you know in your head how many seconds are in a day. Heck, I don't know that. And you might even try to set it up in 1 step like this. But when you go, oh, I don't know how many days are in a second, but guess what? What do I know? Well, I know days to hours and hours to minutes and minutes to seconds. Oh yeah, okay, wait. So I can probably do this in a couple of steps. That's okay. I know days to hours. And I know how many hours are in, how many minutes are in an hour. And I know how many seconds are in a minute. So, okay, I'm gonna, because I don't want to go look this up on Google. I don't want to go grab my book and look up how many seconds are in a day. But I can do it multiple steps because that's what I do know off the top of my head. Now check out how I set this up. My given, my original was days. I'm going to go days into hours first. And I know that 1 day equals 24 hours. And then in step 2, I'm going to convert hours. So I put that on bottom into minutes. So I put that on top and I know 1 hour is equal to 60 minutes. And then in my final step, I'm going to get rid of minutes. So I put that on bottom. And I want seconds, so I put that on top, and that'll be my final answer. And I know that, 1 minute equals 60 seconds. So even though it looks kind of long and clunky, I was just saving myself some hassle because I know days to hours, hours to minutes, minutes to seconds in my head. And now remember, if it's across the top, you multiply, and then if it's on the bottom, you divide. So here's the way I would plug this in my calculator. 2.5 times 24 times 60 times 60. And then that, I hit equals on my calculator, get a number, and then everything is divided by 1. So divide by 1, and you get 216,000 seconds. Now that's what my calculator says. Don't forget, sig figs. 2.5 is how many? 2 sig figs. So my answer needs to have 2. Well, that means I'm going to cut my, or round there. I'm not just going to say this is 22 seconds. No, but that's where I'm going to round. So I'm going to 21, and then my line to the right of the line is a 6. So I'm going to round up. And then you change everything else to zeros. So I'm rounding this up. This is approximately 220,000 seconds. Now, that I'm sure you guys all could have done without me explaining it. You probably wouldn't have like written it all out. You may have just done it in your head or typed it in your calculator. But I'm always going to tell you when you get stuck doing a conversion, I'm going to tell you, go back and do something you know. Set it up, write it out just like I did here. And now look at, compare to what's up here with your pint to quart, quart to liter. It's set up exactly the same way. Using conversions you probably didn't know off the top of your head, but you could have gone and looked them up. Or the problem maybe gave them to you, that 1 quart equals 2 pints and 1.06 quarts equals 1 liter. And I set up pint cancels, quart cancels, liters what I want, liters what I get, multiply across the top, divide on the bottom. It's exactly the same thing. Truly the only difference is the conversion factors are different because it's a different problem with different units, and where those conversions came from, online or your textbook versus your head. That's it. That's it. All right, so here's what I'm hoping you'll do during this. I'm hoping you guys will, I've got 3 example problems here, and I'm hoping you will pause this video one at a time, pause it, you work this out, write it out. Even this one about eggs and dozen, write it all out like I've been showing you this process. Then come back and hit play and compare it to what I did. Okay, so hit pause now, work this problem, come back, check your work, then go to the next one and do the same thing. All right, so that one you should get 62. Technically, we're counting something here, guys, so I don't even know if you'd really apply the sig fig rule. I'm not terribly concerned about that. But you can't even get 0.4 of an egg anyways. So that one's 62. All right, here's your next one. So now try this. Look, you can use the same number. Hit pause, try this on your own, and then come back and check your work. All right, so when you do this one, 5.2 liters is your given. I'm looking for milliliters, so hopefully you just kind of saw what I was doing, even though I wasn't talking through when I did it. I put liters on bottom because I'm getting rid of it. I want milliliters, I put that on top. My equality is 1 liter equals 1,000 milliliters. So I keep the number 1 with the L for liter. I keep the 1,000 with the ML for milliliter. Multiply across the top, divide if it's on the bottom. So 5.2 times 1,000 divided by 1 is 5,200 milliliters. Sig figs, there's 2 here, there's 2 there. As long as I don't put a decimal at the end, that's it, I'm good. I'm good to go. All right. Oh, this one's a challenging one. Pause this one, see if you can't convert this one for us. All right, you guys, so with this one, if you didn't know the equalities, that's fine. You go look up how many kilometers are in a mile, and I need to know how many minutes are in an hour. So 60 miles per hour. So this is a measurement that has two units. Miles per hour means miles on top, hour on bottom. Means you're driving 60 miles per every 1 hour. You can even, if you want to write it out like that, you can even write it out like that if you want. Miles per hour, miles on top, hours on bottom. And then I set up the conversion. Miles was on top, so I put miles on bottom. Hours was on bottom, so I put hours on top. And I want kilometers per minute. So I need kilometers on top. That's why I circled it. It's on top here. And I need minutes in the denominator on bottom. So that's why it's set up there. It's just a game of units. What do I need? What am I given? Put on top what you want to get to. Put on bottom what you're getting rid of. Normally, you know, if you're starting with like miles, or the reverse, I'm trying to get rid of hours in the denominator and I'm trying to put minutes in the denominator on bottom. My equalities, you have to look them up, so be it, or maybe you know it in your head, that's fine too. The 1.61 stays with the km, the 1 stays with mile, 1 stays with hour, and 60 goes with minutes. And so the last thing I have to do here, sorry, I was just starting to type this in my calculator, multiply across the top, divide if it's on the bottom, and you should get 1.61 kilometers per second. Now, sig figs, I wasn't thinking about that when I wrote the problem. This one has 160 without a decimal is just 1 sig fig. So after the first, I have to cut it, but oh, look what I'm gonna do. I'm gonna round up. 1.61 becomes 2 kilometers per second. Okay, hopefully give you a second to think about that. All right. Whoops, what was that? I guess that was, I guess I have, what is it? I have example 4, sorry. I thought I just had 3, I have 4. Okay, so now I've got a problem. Now we're gonna try to apply a conversion that's given to get an answer. So see if you can work this one out. Pause it, pause the screen, try and do this one and then come back and check it out. Okay, so 60 miles per hour is actually giving us an equality. It means you can go 60 miles per every 1 hour. The problem, the given is a distance of 500 miles, and it wants to know how many hours will it take to drive that far. So as you can see right here, I set up a conversion like I've been doing for the last, I don't know, 20 or 30 minutes. The given goes on top, so I put the given on bottom in the conversion. The desired is what goes on top in the conversion, that's in hours. And then I simply need my equality. I can drive 60 miles in 1 hour. So 500 times 1 divided by 60, it's gonna take me 8.333333 hours to go. If you wanna do just 1 sig fig because of this, 5, you could just say it's gonna take me about 8 hours. Okay, now let's talk about temperature. Temperature is an unusual beast. Temperature is not a straight conversion, you know, such as 1.61 kilometers is in 1 mile. Temperature, you use these equations because they're not, it's not the same. And I don't even really want to get into it too much. You just need to use the equations, and you'll always have these equations to be able to use, you know, whether you're doing homework or an exam. Pull out the equation, look, you know, figure out what you need to convert, and then apply the correct equation. And you can see if you're looking for Fahrenheit, you want to find the equation Fahrenheit equals, and that would be assuming you were given a temperature in Celsius. Or if, let's say, like right today outside when I'm recording this, it's 70 degrees Fahrenheit, I want to know what that temperature is in Celsius. Well, then I would grab this equation. Celsius equals, I know it's 70 Fahrenheit, so 70 minus 32, do that math, then divided by 1.8. Keep in mind your order of operations there, guys. Same thing over here. You'd multiply these two first, and then add 32. So you use your equation, and then the only other thing, we have one other unit of temperature, and that's Kelvin. And the easiest way to work with Kelvin is to go between Celsius. So in other words, if I said it's 70 Fahrenheit outside and I want to know what that is in Kelvin, I would first convert it to 70 Fahrenheit, I'd convert to Celsius, and then I would say, okay, once I know Celsius, I add 273 to equal what I want temperature in Kelvin. So play around, give yourself some different temperatures. Here's the temperature scale, and really this is the reason why we don't just multiply by 1,000 or divide by 100 or whatever, that based on the different scales that we come up with this equation. And that's really all you need to know. All right, and then the last thing in this part that I'm going to talk about is density. And so density is a physical property. Again, it's a description of a substance. It relates the mass of that substance to its volume. So for instance, I might have a 1 liter container filled with rocks, and I might have a 1 liter container filled with feathers. The volume is still 1 liter, but the mass is going to be very, very, very different. A 1 liter container of rocks compared to a 1 liter container of feathers, and that's because their density is different. And so density is this equation right here. D equals M over V. However, like I just showed you with miles per hour, if you're given a density, you can use it to convert between mass and volume. And so let me show you what I mean here. Again, hate fractions, right? But if we knew the substance of a density is 1.05 grams per mil, we can actually write that as an equality or as a conversion. If the density of this substance, acetic acid, is 1.05 grams per mil, that means 1.05 grams of this substance is the mass per milliliter, means per 1 milliliter. Just like driving 60 miles per hour is 60 miles per every 1 hour. And so density, if we're given it, is a conversion. We can write it out as an equality, and we can set up, okay, if I start with 5 grams, how many milliliters do I have? So let's just set it up right here like we've been doing. I'm given grams, I want milliliters. So I put grams on bottom so that it'll cancel. I put my desired, or what I want, on top. I want milliliters. And then I need to find those numbers. What milliliter is equal to what gram? Well, that's this right here. You always keep the number with the unit. 1.05 grams is equal to 1 milliliter. Multiply if it's on the top, divide if it's on the bottom. So 5 times 1 is 5. Divided by 1.05, my calculator spits out 4.7619, and still lots and lots of digits from there. Before I circle my final answer for Regis, I look at the measurement. 5 grams, that's 2 sig figs. Has a decimal, so that 0 at the end counts, so I need to take this down to 2 sig figs. 4 and the 7 or 2 cut the line. That's going to round, I'm going to be dropping a 6, which means I round up. It's 4.8. And the unit, always remember, never just a number, but the unit as well, milliliters. Okay, whoops, and yeah, that kind of got cut off, sorry, but that's 4.8 milliliters. And you can work density, you can go from grams to milliliters, from milliliters to grams, or you might even have a density problem where you're given the mass, you're given the volume, you have to solve for density. Then you would just plug them into the density equation, M over V, and solve. Specific gravity, this is the last thing I'm going to talk about. Specific gravity, it's used quite often in medicine in terms of a urine sample, a urinalysis. They might look at the specific gravity of a patient's urine to decide how it compares to water is what it's done, but how hydrated is the patient? Are their kidneys working properly? You guys, urine can be quite concentrated. That has a higher specific gravity. It's got really big proteins and things in it. Or it could be really dilute, lots of water in it, and its specific gravity might be lower. And specific gravity truly is just comparing the density of the sample to the density of water. The density of water is 1. So in other words, the specific gravity of the sample always simply equals the density of that. But it is truly a comparison to water. The units would cancel. So your answer, your number would just be a number, no units, because both densities are in grams per milliliter. And with that, that is your first lecture. If you have any problems, please reach out to me. I'm looking forward to a great class.